So the first speaker of this session is Ulrike Tillmann, and she will be talking about sampling with confidence.
Thank you very much. Thank you very much for the invitation. If somebody knows how to make this bigger, then that would be helpful. Is it that one? Brilliant. And this works. Brilliant. Okay, now that we're set up. Title is there. This is motivated by some work in topological data analysis. So the work I'm going to present is a small part, really, of what we are trying to do in Oxford at the moment. And it's based on some work that started at the Alan Turing Institute in London last year from a seminar with Henry Louis de Kergolay and Oliver Weibhund. Henry is actually in Edinburgh and Oliver is a student in Oxford. And it's based on previous work in this area by Bobrovsky, Weinberger, and Bobrovsky, Oliveira. And I thought I'd put it up here, so just in case I don't say that clearly enough later on. So what I want to do is really introduce, in some sense, topology, homology, TDA, and introduce the main quantities I will be interested in, and then in the second part, specifically talk about the work we have been doing, which is really something in random topology. Okay, so part one. So given data often comes as a point cloud in some Euclidean space or maybe on some manifold. That tends to be completely discrete. We want to associate a topological space. So I'm suggesting here a very standard way to do that is by effectively taking our data points and thickening them up by some epsilon. So that means every point, in my space, in my data set, is thickened up to a little ball, and of course these balls might intersect or not, but that gives me, and the union of them at least gives me something topological to work with. But of course this is now very difficult to analyze if you want to do computing, and so we immediately, in order to do computation, we go back to something that's more combinatorial. And there are two standard ways to do that. One is the so-called check complex, and the other one is the Vittorius-Rips complex. Both are very closely related in terms of what they represent. The check complex is a more faithful representation of the space that I have here, and I'm going to be precise in a moment, while the Vittorius-Rips complex is actually computationally much more easily tractable. So, right, let me actually just go on to my next slide. So what is a check complex? We look at these open balls. Well, I first construct a graph. The underlying graph is built on the vertices being just the point cloud that I started off with. Okay, so I had points in my data cloud, and those are going to be the vertices of the underlying graph. And then I add an edge for whenever the two balls that I had around 2 points actually intersect. So there are different sort of normalizations, but here basically the point P0 and P1 are going to form an edge if and only if actually their distance is less or equal to 2 epsilon. Okay. So that's an edge, and now the question is higher simplices, so triangles and tetrahedra, etc., are going to be added to this graph, and there are two different ways of doing it. In the check complex, what we do is we look at all these balls that we had around different points. Say, if you look at a triangle, you look at the the corner points of the triangle, look at the ball around them. If all balls intersect, then you add that triangle basically to your simplicial complex. And similarly with higher dimension, if all the epsilon balls around these k+1 points intersect, the intersection is non-zero, then I add sort of the tetrahedral or higher dimensional k-simplex to my simplicial complex. So for computational things, it's important to understand how we go from higher simplex to the boundary. And of course, the boundary is just given by this combinatorial thing. Is if I just delete the i's point in this set, then I get something that's still intersecting, right? If I take out the i's ball, then of course the remaining set will still intersect non-trivially, and that defines for me sort of the I space to this set I'm given. Okay, so the Vietoris-Rips complex is very similarly defined. I'm not going to use it very much. The reason it exists in this sort of setting is that it's quite hard, quite expensive to compute all these intersections, whether they're empty or not. So in the Vietoris-Rips complex, one just sort of takes a clique complex on the graph that I defined here. So the Vietoris-Rips complex starts off the same way. It has vertices set P and edges whenever 2 points are less than 2 epsilon apart. But then the higher simplices, I'm just going to add a k-simplex whenever I see a complete graph on k+1 vertices. Okay, so that's then a very simple to compute. And a very precise comparison when these things give me roughly the same thing, but I'm ahead of myself because now I have these complexes and I want to associate to them some sort of algebraic signature that can be computed. And that's really the next step. Now you started with your point cloud, you associated the simplicial complex, which is some combinatorial data, really. And now I want to extract something that is also independent somehow on the underlying topology element. So this is what we take from algebraic topology. We are told that we should look at, whenever you have such a simplicial complex, so I didn't define what a simplicial complex is, but we had the example, you have vertices, you have edges, triangles, tetrahedra, and you build up some sort of complex that way. You think of it maybe geometrically or purely combinatorial. And so this chain complex is now, well, think of it as a vector space, or you can also work over the integers. And you just take the n simplices as the basis of your vector space, of the n chains. This is called the n chains. And you have maps between them. Namely, for every simplex, n simplex, you just associate to it its boundary. So all the alternating faces of its boundary, the alternating sum of its faces. Apologies. Okay, so we had a very specific formula there for the check complex, and in general, that is part of the data for a simplicial complex, of course. And the key observation when you do that is in a simplicial complex is that if you take the boundary of a boundary, that's always empty. Okay, if you just think about it, the boundary of a disk is a circle. The circle doesn't have a boundary, and that sort of is the paradigm in this sort of setting. And so that means actually that the kernel, so the things that go to 0 under this map, contain the image of this map. And so that makes sense then to form this quotient group, quotient vector space, depending on what you're talking about. And so this is the key thing, and this really then measures in how much things that are cycles, so things that don't have boundary, are actually boundaries themselves. And this is quite an important idea that also comes up in other situations in mathematics, of course. And the Betti number, a very algebraic thing here, is just the difference of dimensions of the image and the kernel. Okay. So in our situation, remember I started off with this point cloud associated as space, and then we had these two different ways of forming a simplicial complex from that data. The situation is such that the check complex theoretically is preferred because of this so-called Nerv lemma. When we are working in a manifold or even in Euclidean space in particular, then we always have that the check complex, the homology that I just defined for you, is actually the homology of the underlying space. So there is something in algebraic topology that's called the homology of a space, and it's completely independent on homotopy, so I can squeeze and stretch and push the space, and the homology doesn't change. And so it's a very important invariant of the space itself. And here we have that this very combinatorial thing gives us back exactly that quantity that you might want to associate to this space, to the underlying space, which is just a union of all those epsilon balls. The Vittorius-Rips complex doesn't quite do that, but there are estimates how far out it is essentially is. So here you can see it sees this particular hole here, while this hole is exaggerated in the check complex, is not even visible in the Rips complex. And similar with this tiny hole here. It's visible here, but no longer in the Rips complex. So it's those holes ultimately that actually homology detects. Namely, here we have, you can see, here we have actually, if I just look at the boundary of the triangle, that is something that is in the kernel. It doesn't have any boundary, but yet it's not the boundary of something itself. So that gives me something non-trivial in homology. Okay. So in particular, this means, going back to the topology, and you might have seen this already, the check complex would actually compute the topology, homology of this torus, and the underlying torus, the interpretation, of course, once again, as I said just now, here we have actually these two, no longer works. Oh, yeah. We have these two circles in dimension 1. They don't have any boundary, so they define for something non-trivial in the homology, and they are not the boundary of a disk or something, some other surface, and so they are something non-trivial in the homology. Okay. I couldn't quite resist pushing this picture in. It is actually the 100th anniversary of Emmy Noether getting her habilitation. That's a mini legenda, so her permission to teach at Göttingen University after much effort by Hilbert and Klein. The reason I put her in here, mention her here, is that I hadn't really quite appreciated myself, but she had actually a huge influence on topology, in the sense that she pushed, in conversations with Hopf and, no, the name, Alexandrov, who were visitors at, long-term visitors at Göttingen. She pushed the idea that you shouldn't just look at Betti numbers. Betti numbers are really, then interesting, and I just repeated the mistake in some sense. It's just a number. But once you consider actually homology groups, you're much more flexible. And that's her point of view, her input, and indeed both Alexandrov and Hopf sort of start off their books on topology by acknowledging her and pushing this point of view. And indeed, this idea that we now have groups or vector spaces, if you like, that means that if you have now maps between complexes, that also allows you to have maps between the homology groups. So the functoriality becomes now completely natural. And this is, of course, what is done in persistent homology. Persistent homology is sort of the fundamental tool in data analysis, topological data analysis. There are several names I should name, certainly Edelsbrunner and Carlson, but many others. So what is the idea here is that, remember, we had our check complex. I had to pick an epsilon, so my balls were of size epsilon. Now, that was sort of random, or I just picked it, and you need to know when you choose a sensible epsilon, or what is a good epsilon. And the persistent homology says, well, I don't know. I'm trying to understand this data set, and how should I know what a good epsilon is? So let's just take all of them and see how the topology of the underlying simplicial complex changes. So here, indeed, you see the, there we are. We start with a point set, so epsilon is 0, and then we have increased it to epsilon 0.6 here, whatever scale we are on. So we're increasing it slowly, and of course, as we increase, we see sort of here and here the circular nature of my point cloud. And of course, if my epsilon is too big, then we just get a big blob. And this is now tracked down. These blue things give me the connectivity. That's H0 is just counting the connectivity of our spaces. So of course, at the beginning, it's very disconnected. So I have lots of bars. At this stage, I lose a few. And at this stage, I'm already all connected. So, and then my space, of course, stays connected, my simplicial complex. That is the connectivity, so dimension 0. Dimension 1 counts sort of the cycles in my complex and the 1 cycles. And here we have clearly a 1 cycle, one-dimensional simplices with no boundary and not being filled in. And so we get this bar, but it vanishes as soon as my epsilon gets too big. So this is the signature that you might want to be interested in. And it's, there are many freely available programs that compute this sort of persistence signature. So let me just say persistent homology, sort of two key things one needs to know about it. One is that indeed you can always find a basis of the homology so that you can push it through. You can see how it changes as you increase the epsilon. And the second is the stability, namely, if I change a little bit the point cloud, move things around, so within the Hausdorff measure of the set, then indeed the persistence homology also only changes a little bit, and there's a metric on these barcodes, and I can make that precise as being continuous. Okay, so what I said here is very much sort of the paradigm of how you explain why homology might have something to do with data and how you use it. Of course, in every application, you have to adjust your method to what you have. We have a center on topological data analysis in Oxford, and at the moment we are looking, for example, at vascular data in a tumor. And so there you actually just work with a graph and you filter it from the center out. So that's a different sort of approach. Somebody is looking at some data with Spotify, and there you look at cubical data sets and so on. So there are different ways of applying the same idea, and you have to adjust your method, of course. Okay, so this brings me, however, to the second part of my talk, because if you look at the data set, then you want to somehow see the interesting, unusual features or maybe you want to find the paradigm, but basically you would want to compare it to something that might be a null hypothesis. And so random topology is actually even a bigger sort of subject. It really asks the question, what could I expect? What's the homology randomly of a random set, of a random simplicial set? And so these questions go back, actually. I mean, sometimes what we have been doing at the Turing Institute, it sort of goes back into 3 different strands of random topology. And indeed, this morning we saw already some of that. So random graphs have been studied for, well, I guess 60 years. So Erdős-Rényi actually started off with a random graph where you have n vertices and you have a probability p, and you put an edge between any 2 vertices with probability p. And then you can ask yourself, for example, the question, when can I expect the graph to be connected? So H0 being one dimension in our setting. And the answer is, indeed, that happens when the probability p is roughly log n over n. So that's very much a phase transition. Above, you expect the graph to be connected. Below, you expect to have many components. Then, for many applications, of course, a random graph is not what you would expect. For example, if you have a network of people, or there's a constraint given by the geometry. And so Penrose, in 2003, his book, studies random geometric graphs. So in this case, you take P actually a subset. That doesn't look right. You take P a subset of Euclidean space, R to the D, and then you have a distance between points, and you connect them whenever the distance is of a certain fixed radius, in this case r, here log n over r to 1 over d. If it is at this threshold, then again you can expect that the graph is connected, and otherwise it will have many components. Okay. So as a summary, phase transition can average number we have a phase transition when the average number of edges at a vertex, so the degree at the vertex, is roughly log n. Okay. And in terms of homology, it just means connectivity, of course, is H0, just being one-dimensional. Okay, so that's random graphs. There's, of course, another idea that has been around, namely, just take your points and take epsilon balls, and there's a sensible question, given any Riemannian manifold, when do you cover all your manifold? When do you fill it up? So this has been studied in a paper in ACTA 1977 by Flatto and Neumann, and they look at d-dimensional unit volume closed Riemannian manifold and take n uniformly distributed points and take radius r balls around these points. And so when do these cover the manifold and the threshold? Again, it's very closely related to what we said before. It's log n over n and then square root of that. Okay, so translating that back into homology, for a closed manifold, there's something called Poincare duality, and we know that closed manifolds have, in top dimension, they have homology that's exactly dimension 1. And as soon as you have a hole, then the dimension, the homology would be trivial. So covering here just means actually that the top dimensional homology are the same. That's a translation for our purposes. Okay, So then we have sort of 0 and we have d dimension. You can ask what happens in between. How closely can we recover sort of the k-dimensional homology? So, and then, of course, there you have to understand, first of all, I mean, you first have to think about a random simplicial complex so that you can ask the question accordingly. And there, again, you have the two approaches. One is sort of generalizing the Erdős-Rényi approach. You just give yourself some random set of, you take n vertices and the probability measure, you build a graph, the Erdős-Rényi random graph, and on top you add simplices whenever you happen to see a clique. So really, we just take the so-called flag complex on the graph that Erdős-Rényi constructed. And this has been studied, and indeed, Lenius and Mishulam have a study trying to understand when, for example, these are connected and they are homologies. And similar, I think that's quite an interesting one. You can also try to study groups this way, because every group is the fundamental group of some 2 complex, and you can get that way a notion of a random group. So Kale, in the Annals paper from 2014, he actually manages to compute the homology, the case homology now, or gets the threshold, I should say, of these random flag complexes. And it's precisely when P is, well, this quantity here. So the interesting part to note here is that actually this depends on K itself. So we do get different behavior in dimension 0, in dimension, the top dimension D, and in every dimension K in between. Okay? So having done this for this sort of Erdős-Rényi random model of simplicial complex, you might ask yourself then, what happens for the geometric random simplicial complex? Okay, so again, there are many models, but I'm going to concentrate on the check complex, and I hope I motivated that before. So the random check complex is, of course, built the way we had it before. We think of a d-dimensional unit volume smooth Riemannian manifold M, and we take a Poisson point process with expected density n on M. And so we want to understand some sort of limit, some sort of threshold that recovers the case homology. Okay. All right, so here's the result that Bobrovsky, Weinberger, and Bobrovsky, Oliveira have achieved in the last couple of years. To say it precisely, I have to define a few entities. So here, this lambda is, okay, WD is just the volume of a unit ball in dimension D, a Euclidean ball. So WD times R to the D is just the volume of a ball of radius R, and then the expected number of points that I have from my from Poisson distribution in such a ball is then n times the volume, and that's given there. So now I take the check complex on Pn with radius r. So that's exactly what I constructed before. We have the points, we have balls around them of radius r, and I build the complex whenever I have a k simplex whenever I have non-trivial intersections of k plus 1 balls. Okay, so with this setup, we now can ask the question, when is the homology, the case homology of this check complex the same as the case homology of the underlying manifold? Okay, so the answer is, the best answer so far is, we say with probability 1, we know that if the density, the expected number of balls in an R ball is actually log n k times log n plus some arbitrarily slow growing function of n going to infinity, okay? Some error term, basically. And on the other hand, we have the split, right? So we don't know whether this is sharp, and indeed we expect it's not. But we do have also an lower bound, namely, so it's just a factor of 2 here, missing, namely, as soon as lambda, as soon as I don't have enough points sampled, then I actually expect that this is not going to hold. Never. Okay? So this is quite a striking result, especially this second component here. Again, clearly says that actually this threshold is likely to depend on the dimension I'm looking at. Yeah, well, it is going to depend on the dimension I'm going to look at. Okay. Now, Bobrovsky and Weinberger did this first for torus, and then Bobrovsky and Olivia generalized it for any manifold, Riemannian manifold. And there was an open question also mentioned in a survey taken by Kale and Bobrovsky. What happens when you have boundary? A lot of our manifolds have boundary, and how does the situation change? And this is exactly what we were able to show, that indeed most of the arguments go through in the boundary case, but you get a slightly different result, and you get some new features, if you like. So the result, again, you take M to be unit volume, smooth Riemannian, but with boundary. Okay? And again, you look at when is the case homology of the check complex the same as the case homology of the manifold. And in this case, we get actually a slightly different leading term, namely 2 minus 2 over d, so nearly twice as big as the one without boundary. Here again, we get not k, but 2k. And for the lower threshold, unfortunately, we don't get the dependence on k, so that tells us there's probably room for improvement. And but actually, I think there's also room for improvement probably for this sort of this threshold here. The question is just what is it? Okay, so maybe I just say a few words. Right. Okay. So how does one even approach this sort of question? And there are many ingredients that come into, and I should say most of them were already there in Weinberger and Bobrovsky's work. So the main idea is actually to start with Morse theory. So Morse theory is a well-known theory which tries to approach manifolds and tries to understand the homology by looking at a function, a height function. So actually, oops. So the picture here is you have some sort of manifold here, and the height function goes to R, call it F, and you look at the singular points of this height function. Okay? And you ask yourself, you first assume that these critical points are non-degenerate. That means the Hessian is full rank. And it sort of tells you how many flow lines are going down and how many are going up. So here I just have 2 up. Here I would have, if I did this nicely, I would have downwards and 1 upwards maybe. And here we have downwards ones. So the Morse theory then tells you, well, as soon as I hit this, I get a point, so the topology changes, but it doesn't change until I hit something else, and I get 2 points, 2 connected components, and then nothing happens until I hit the next critical point, where actually those 2 critical points before, the 2 components are merged in this case, and then nothing happens until I hit the following. So topologically, nothing interesting happens until I each time hit a critical point, and one can use this in Morse series to actually form a new complex that computes the homology by taking the generators to be these critical points of the right, in the right dimension. Namely, I'm thinking of these things are having critical index 0. This will be 1, and this might be 2 if I'm thinking of this as a surface. And so I built up, actually, from this analytic data, another complex, which is the Morse complex, and the Morse theorem tells me that that complex computes for me the homology of M. Now, the introduction of such a new critical point, basically 2 things can happen. Either I get a new homology class in that degree of the index, or, like in this one, I'm actually killing one below, because these 2 connected components, which gave me 2 elements in H0, are now connected, and so that's, at this stage, I'm actually sort of killing one of the homology generators from one below. So this is exactly what one now uses, and the height function in our situation, remember we are filtering our space with balls that are growing with bigger radius. So you can think of it as growing from lots of points, with the radius growing at some point reach, of course, the whole manifold. And the distance function, no, wrong way. There we are. The distance function, I take it squared, and so given a point y, I take just the distance of that point y to all the points in my point cloud. Okay? Now, this isn't quite smooth, but it is nearly good enough. It's of what's called min type. And indeed, there's a version of Morse theory developed by Gershkovich and Rubinstein in the 80s, which sort of allows to go this Morse theory idea through for these min-type functions. And so then it remains to understand what are the critical points of this function. And indeed, if I have 2 points, and I look at, so these are points from my point cloud, and I look at a point y, well, this one has, of course, distance function to P1 is actually going to be smooth, so I'm not going to worry about that point, that's fine. It's smooth and there's no critical point. However, when I'm actually right in between these 2, this will be a critical point. And more generally, if I have a 3rd point here, and this is supposed to be equal distance, then I get a critical point possibly here. So indeed, I'm going to get a critical point whenever I have, in dimension 2, whenever I have 3 points with a center C, so C will be a critical point, and these are points from my point cloud. Whenever I have a configuration like this, C is inside the triangle, and there's no closer point. All the other points from P are outside. That's exactly when I get a critical point. If C happens to be outside of the triangle, then it doesn't count. If another point is inside, it doesn't count. So the task then is to understand these sort of critical points for our distance function, for our manifold, for our point cloud. So what is the overall structure? First of all, I find small but large enough R so that actually I have a covering of my manifold, because once I have a covering, I know the check complex will recover all of the manifold, and therefore all of the homology of the manifold. Then I find an R close enough maybe to R0, such that I don't expect new critical points as I increase from R to R0. And then if that is so, and then I know with high probability that the case homology of my manifold M will be, of course, the case homology of the check complex with radius R0. And because I know extra critical points, it will also be the homology of the check complex with radius R. And there's something called Palm's theory, which estimates somehow, which helps estimate these points that we have, critical points. Okay, so that's already the old story. I have 1 minute, I think. Let me say, what is the new idea in some sense in this work where you have boundary, where you allow boundary? And already in the old work, it's sort of a little bit subtle. So somehow the covering is not so difficult. The tricky one is, in some sense, the lower bound, and to get a sharper lower bound. And this is here what happens. So, so we are here actually seeing an open ball, and the cut part is supposed to be the boundary, okay? So we have here sort of an annulus. Think of the outer one as our R0, where we are safe and everything is done. And look at the inner one as our R. So here you see when this epsilon or this R is small, then it covers sort of this smaller ball with this triangle that effectively, having a simplex, having a critical point, corresponds to such a triangle, and the effect of raising my R is sort of, in this case, gives me this critical point and gives me this cell. So here I get actually an extra hole, namely the hole between the shell of the smaller ball and this red triangle. There's a hole of dimension 2. Now that hole topologically goes because here I can go in and out of that hole. So it's no longer there. It's no longer closed. So it doesn't give me a homology class. So really, here we have actually a phenomenon that when my epsilon is too small, I have more homology than I should. Okay? And that one has to account for those. So here is the same situation. The other one already occurred, of course. And here we have we need to also understand how exactly this triangle sits in our double shell. Because, of course, if it is not virtually tangential to the boundary, it doesn't. There's no hole here. Now I can go in and out freely. There's no hole, no cavity. And similar here, of course. So we need, in order to account for these boundary fake classes, we really need to understand, in some sense, the measure of all these critical points, not just on the boundary, but when they are lying in something that is a proportion of the boundary, roughly speaking. So if then something is through here, it will cover things up, and roughly speaking, something tangential to the boundary of M. And so, yeah, I think my student had fun creating these pictures. So I stop there. Thank you very much.
So does anyone have any questions? Yes?
So in terms of the persistent homology, would this make a prediction what part of the persistence diagram would be most interesting to see?
That's a good question. It's not immediately that easy. There's work actually by Bobrovsky, Kale, and Straber, which tries to understand what's the random persistent homology. So you have to sort of I don't know, upgrade or do additional analysis to get there.
So in the case of a point cloud from data, you don't actually have a manifold, you just have the check complex, and you'd like to be estimating some statistical manifold that the data is on.
Right.
So now in your case, when you get past the phase transition, the check complex has the same homology with probability 0, what does that tell you about the point cloud? So you've still got a mapping from the check complex. So here you do have a manifold. You've still got a mapping from the check complex to the manifold, so you get some mapping on homology. Can you say anything about that mapping in that case? I mean, is it surjective? Or?
So the check complex does actually compute the. I mean,
I'm sorry.
You do get a manifold actually.
I muddled up two observations there.
Okay.
I was trying to map. The simple question is, in the case where you've got the manifold, you're past the phase transition, you've still got a mapping from the check complex to the manifold, but now the homology is not the same. But it's
no, it is. If you are in that, the map is going to be an isomorphism.
So in one of your cases, the probability was 0 of the homology.
So for the lower, when you're in a lower threshold, yes. If you don't have enough points, if the density is too low, then with probability 0, you're not getting the right homology with this map.
Yes, because you're incorporating.
Yeah. So I mean, from a purely data science
that
point of
sense.
view, there's a criticism here.
Yeah.
These degrees are very high. And indeed, we're just trying to do now some experiments to understand, for example, whether there's a better threshold, because we only could, both upper and lower, one would like to have just one threshold, and then probably asymptotically there should just be one. And we're just trying to do computer calculations, and it's not easy, right? Because the thresholds are quite high. So that's a clear criticism, but I think we need to know also the theory behind it and get a feeling for what we're doing.
So staying in the timetable, I guess we could save the rest of the questions for a coffee break.
Okay.